Hello, in this video I'm going to solve a problem on classical mechanics. This is a problem chosen from this book, problem 4.18, page 100. Let us read the problem first. A body is released from rest and moves under uniform gravity in a medium that exerts a resistance force proportional to the square of its speed and in which the body's terminal speed is capital V. Show that the time taken for the body to fall a distance h is capital V over g times cosine hyperbolic inverse of e to the power of g h over v squared. In his famous, but probably apocryphal, experiment, Galileo dropped different objects from the top of the Tower of Pisa and timed how long they took to reach the ground. If Galileo had dropped two iron balls of 5 millimeters and 5 centimeters radius respectively from a height of 25 meters, what would the descent times have been? Is it likely that this difference could have been detected? Use the quadratic law of resistance with C equals to 0.8. The density of iron is 7,500 kilograms per cubic meters. And here C is the drag coefficient in Reynolds formula, yes, or in Reynolds law. Okay, so let us go to the board and try to solve the problem. Okay, so if I want to solve this problem, let us say that, okay, the particle is released from some height from the ground, for example, on top of the Tower Pisa, and this is the ground level. Okay, so I will set up my coordinate system in this way. So I would say that let me take the origin of my y-axis, and I want to take the y-axis in this direction, the positive part of it in that direction. And then my particle is released from here. So what does it mean? It means the initial velocity is actually zero, or the initial speed is zero. And then I wait for t seconds, capital T, and of course this particle will cover some distance, h, and I want to show that there is this relation between that time and that h that is covered by the particle during that time. Okay, so for example, let us assume that this particle reaches somewhere, and then to denote this particle, so this is the position vector of my particle after any time t, for example. And then there are two forces acting on my particle, yes? So let me draw the free diagram here. I have the force of gravity, the weight of the particle, this is the vector W, and I have a drag force due to the air resistance. So let me call this one capital D. But according to the problem, the magnitude of vector D, which I represent by just symbol D, so D by definition, I mean the norm of this vector. This is given to be proportional to the speed. Speed means norm of velocity squared. So under these conditions, we want to solve the problem. Okay? So what is the position vector of my particle? Let us say that after time t, the particle has covered distance y. So the position vector, if I call it capital R, the position vector reads like this: y times y hat. Y hat is the unit vector on this. Of course, here I am insisting to work with vectors, but of course you don't have to, because that's a one-dimensional problem, but it doesn't hurt, okay? So what is the total force? The total force here is equal to two forces. One, the force of gravity plus the drag force, okay? So the force of gravity is exactly pointing in the positive direction of y-axis, and the magnitude of this is just m, the mass, times g, the gravity acceleration. So I can write it as mg, but I have it vector form, so I will write y hat, because it's pointing in that direction. But the drag force is actually pointing upward. So what can I write? I can write It is proportional to speed squared. So here, what I will do, I will write it as minus k, and then I can write v squared, okay? But I want to get rid of m, so it doesn't hurt if I bring the constant proportionality constant to be just simply k times m rather than just k, okay? And then I have the speed squared, and then I will have y hat, yes? So the magnitude of the drag force is proportional to speed squared, and it is pointing upward, so it should be in the direction of negative y hat. Okay. But what is this one? This is a speed. Speed is exactly the magnitude of the force, magnitude of the velocity. So the velocity, by definition, is r dot. But I have two things here, but this is constant, so I just take this one, so it becomes y dot y hat. Then it means norm of vector v is equal to the absolute value of y dot. But norm of v is just what we call speed. But do I need the absolute value in this case? No, because in this setup you see that y is increasing by time. So y dot is a positive quantity, and I don't need the absolute value, so this becomes just y dot itself. So v is exactly y dot. So now I write Newton's second law. So Newton's second law tells me that the mass of the particle multiplied by the position vector double dot, the second derivative, is equal to the total force, and the total force, I can factor a y out, so it becomes mg minus km v squared y hat. Okay, so might be, it seems that I am making the problem a little bit hard. So if you are okay with working and understanding the signs of forces in one dimension without invoking the vector calculations, that's of course completely okay. But what is r double dot? So r double dot here is y double dot y hat, okay? But this means that I have m y double dot y hat equals this combination y hat, so I just don't need to have y hats. And then this is now clear why I put an m here, because now I can get rid of that m. Of course, if you don't put that m there and then work with k, it works out fine at the end. But here, the algebra becomes a little bit simpler, so this is what we have. Okay, so this is the differential equation governing this motion. And I know that because I want to connect t and h, it means that I have to be able to connect y to t, time, yes? But now you see that y is not connected directly to time, okay? So what can we do now? Before continuing forward, let me bring this capital V in the problem. The capital V is the terminal velocity. So what does it mean? It means that when you release this particle actually speeds up. When it speeds up, because the drag force is proportional to the speed squared in the opposite direction, this drag force will increase, and eventually this will cancel the the acceleration due to the gravity. And at that moment, there are no force acting on the particle, so the particle can continue with the constant speed. That speed is called the terminal speed. So in order to find capital V, which is terminal speed by the problem, I have to equate the drag force and the force of gravity. The magnitudes are okay. So what I will have, I will say that at the moment, then when the particle reaches to this uh, terminal velocity, this is the magnitude of the drag force. It should balance out the force of gravity. And this m and that m are cancelled, so I see that v squared, kv squared is equal to g. Okay, because you see that there is no k in the problem. Instead of k, they want to bring v squared in. So here I can say that what k is nothing except g over capital V squared, so we will need it in the future. Of course, if you want, you can immediately plug this in, but if you don't mind, let me plug this at the very end of my calculations, okay? Another problem is that here, I want to use a trick by substitution, because you remember that V itself is y dot, okay? So if V is y dot, then y double dot becomes just v dot, okay? But what can I write for d v dot? I can write d v dt, but I can write dv dy by the chain rule multiplied by dy dt, which is again y dot. So this becomes y dot dv dy, but y dot is again v, so simply this becomes dv dy. Okay, so I go back into this equation. Instead of y double dot, I can write this. So it becomes v dv over dy. And on the right-hand side, I have g minus k v squared. And that is a very simple separable differential equation. How can I solve it? I can say that v dv divided by this combination, g minus k v squared, equals to dy. And now everything is ready for integration. Yes, I integrate, but of course I know that when I integrate, I will connect y to v. What I need at the end, I need to connect y to time. Okay, but that will be the next step. So let us calculate this one. I integrate the left side, okay, v dv over so if you don't mind, we can continue like this. K v squared, and then I will integrate the left-hand side, but I know that after integration is done, I will have a constant of integration. So in principle, you know it from your differential equation course. But this is very simple because the derivative of the denominator with some extra coefficient appears here. Okay, so if you take this one in your head, u, okay, so if you want, I can write it here. So if I take this one to be u, I differentiate everything with respect to v. So here it becomes minus 2kv dv is equal to du. I am interested in the combination v dv there, so I divide everything by this expression. So minus 1 over 2k du. And then I go back there. This integral becomes integral of the numerator, which is minus 1 over 2k du, and the denominator is just simply u. And this is a very famous integral, so it becomes minus 1 over 2k ln of absolute value of u. And this absolute value is in principle essential to consider. And then I replace u with that expression, so this becomes minus 1 over 2k ln of absolute value of g minus kv squared. Okay, but is this expression positive or negative? So this is a typical velocity, this is the typical speed of my particle during its journey, but you know that v, which is the terminal speed, is the maximum possible speed that the particle can attain. Okay, so what does it mean? It means that whatever v is, whatever little v is, this is always smaller than capital V, or at most equal to it. Yes? Okay, then what happens if I multiply everything by minus k? So so let me square it first. So I square it and then multiply it by minus k and add g to it. So I multiply it by minus k. So I have to flip the sign and I add g to both sides. Yes? And then this combination is 0. So this is non-negative. So whenever, of course, when it is non-negative, I don't need this. I don't need the absolute value sign. But this analysis is essentially important to know about it. Okay. So this becomes minus 1 over 2k ln of. I can just replace it with just parentheses. Yes. Okay, but the integral on the right-hand side is just simply y, And then, of course, I add a constant of integration. So if I plug everything back there, so if you don't mind, let me write it here. So the left-hand side becomes minus 1 over 2k ln of g minus kv squared. On the right-hand side, integral of dy becomes simply y. Then I have a constant of integration, so let me call it capital A. In order to find capital A, I know that the initial velocity or the initial speed of my particle is 0. So it means that if y is 0, because when I release it at that time, at that location, y is 0. When y is 0, v is also 0. So using that, I can fine-tune this constant of integration. So I replace v with 0, y with 0. It becomes minus 1 over 2k ln of g equals to a. So this is the constant of integration. I put it back here. So what will happen? It becomes minus 1 over 2k ln of g minus kv squared equals to y minus 1 over 2k ln of g. And what I want to find, I want to find the relation between y and v directly. So I move this to the other side. When it goes to the other side, it becomes positive 1 over 2k. I factor 1 over 2k out. Ln of g minus ln of that. I use properties of ln. I can write it as ln of g over g minus kv squared is equal to y. Yes? So I move this to the left, it becomes positive, then I factor 1 over 2k out, it becomes ln of g minus this ln. But ln of g minus this ln, it becomes ln of the division. Okay? And then I multiply everything by 2k. So this becomes ln of g over g minus kv squared is equal to 2ky. But then it means that g over g minus kv squared is e to the power of 2ky, because I want to find v in terms of y. So what I can do, I can find the reciprocal. So g minus kv squared over g. Then the reciprocal of this is e to power minus 2ky. Then I multiply everything by g. It's just very simple algebra, okay? Okay, so I move this to the other side, I factor a g out, 1 minus e to the power of minus 2ky, and I move this to the other side, so it becomes kv squared. And I divide everything by k, so if you don't mind, let me just do it here. So k goes down there, and then I take a square root. When I take a square root, it becomes plus or minus the square root of this one, but v is the speed. And we discussed about that before, so I don't accept the negative sign, I will accept the positive sign. So v becomes the square root of g over k square root of 1 minus e to the power of minus 2ky. So this is the relation between v and y. So if you are interested to know the speed of the particle when it has covered the distance y, you put y there and you find v. But that is not exactly what we want in this problem. We want to connect time and the distance traveled. Yes? So then it becomes simple. What was y? Y was defined to be y dot. Yes? So instead of v, I put y dot equals to square root of g over k square root of 1 minus e to the power of minus 2ky. But y dot is nothing except dy over dt. Again, dy over dt is this one, so that is also a separable differential equation. So I bring this square root sign down. I want to separate my variables. And then I put dt here, so it becomes square root of g over k dt. And then I start integrating again. So I will integrate the left side, I integrate the right side, that's a constant, I pulled it out. But of course, I have to take care of the constant of integration. So the only challenge now in front of us is to calculate this integral. Yes, and that's also very simple, yes? How can I do that? So might be the trick that we use here. So let me do it here. I will do like this. Instead of that one, I write it e to the power of minus 2ky, and then e to the power of positive 2ky minus y. Yes, what I did, I factored this expression out, and this is valid. Why? Because if you multiply this back, it becomes 1, and if you multiply this back, it becomes exactly this. So what I have done is correct. But what is the benefit of that? This square root sign that you see here will help me to get rid of this factor of 2. So this will come out without this factor of 2, and this negative sign will help me to move it upward. So then it becomes what? N equal e to the power of e to the power of ky dy divided by square root of e to the power of 2ky minus 1. But this is simple now. Why? Because if you take e to the power of ky as your new variable, so if you don't mind, I don't know, let me call it L, then I differentiate the left-hand side becomes k e to the power of ky dy, the right-hand side becomes simply dl, but in order to find this combination, I need to divide everything by k, so e to the power of ky dy becomes 1 over k dl. Okay, so I will continue here. This becomes unequal. Instead of this one, I can just simply put this dl. And if you don't mind, let me pull 1 over k out, yes? And then I have square root of L squared minus 1. But that's a very famous indefinite integral. This is cosine hyperbolic L. So this becomes 1 over k cosine hyperbolic inverse of L. Okay? And then what I will do, I will replace L back in this problem. So if I want to combine everything now, the left-hand side becomes 1 over k, yes, and then I have cosine inverse, cosine hyperbolic inverse. Instead of L, I put e to the power of ky. This is the left-hand side. The right-hand side, I have this factor multiplied by t, but plus the constant of integration. Let me call it b, because I used letter a before. And then, of course, as usual, you need to find b first. How can I find b? I know what happens in the initially, yes? At the very initial time, when t is 0, of course, the distance traveled is still 0. So it means that y0, t0 should fit this equation. Okay, so if I put 0 here, it becomes 1 over k cosine hyperbolic inverse of e to power 0, which is 1, equals to this vanishes and b happens. But cosine hyperbolic inverse of 1 is just 0, because cosine hyperbolic of 0 is 1. So this is just 0, and then it means that b is 0. If b is 0, I don't need to look here, because I am looking for time t. So time t is equal to, I multiply by the reciprocal, and then I have 1 over k, square root of k over g, and then I have cosine hyperbolic inverse of e to the power of ky. Okay, so this is more or less the relation that I want. This is the relation that connects the distance traveled y to t. Okay, if I want to write everything in terms of what the problem asks, so let us see what we are supposed to do. Okay, so I don't think we need this part. So if you don't mind, let me clean here and continue here. So the time from the beginning, I called it t, and the distance traveled in the problem, they called it little h. So what does it mean? It means that if y is replaced by little h, this t is the t demanded in the problem, so which I called it myself capital T. Another twist of the problem is that you remember k was not given in the problem from the beginning, but I could calculate k from here. K is g over v squared. So in that problem, I replace t with my capital T, I replace y with little h, and I replace every appearance of k with this combination. So then what will happen? Then t becomes equal to, as you see, 1 over k becomes v squared over g, and then I have a square root of k over g, What is k over g? K over g square root of that, it becomes 1 over v. And then I have cosine hyperbolic inverse of e to the power of ky, kh, but k is again that one, so it becomes gh over v squared. And then of course this v and that v are now cancelled, and then you get this back. Yes? So that's okay. So what we did is actually true. But now there is another part to this problem that we want to understand, and to see that if Galileo could actually, if he really did that experiment, could he detect the difference between descent times of two separate balls? One ball with a radius 5 millimeters and the other ball with radius 5 centimeters. So it means that one ball has radius 10 times larger than the other ball. Okay, so you know what happens if the radius of one ball is 10 times larger than the radius of the other ball, because the volume of a sphere is proportional to the third power of the radius, so it means that the volume and consequently the mass of the bigger sphere is 10 to power 3, 1,000 times larger than the other one. Okay, probably we could, based on intuition at that time, people probably expected a very big difference in descent times of one heavy object, 1,000 times larger than the other object. But now let us see how the calculation works and how it is going to, how can we calculate this? Okay, so one thing that in this calculation is important to know is the magnitude of the Dirac force. So by Reynolds' law, if the Dirac force is proportional to square of the speed, then the formula is C, the Dirac coefficient, and rho of air. Okay, I'm just using an empirical formula that we have access to nowadays, if the Dirac force is proportional to the square of the speed. So this is the density of air, and this is the constant, which in this problem is given 0.8, and then I multiply it by the radius, and then I have radius squared, and then I have v squared. V is the speed of the object. So this is the force experienced by, say, for example, a sphere of radius r moving in the air with density rho a and the speed v. Okay. Okay. So now, of course, let me write this v for the time being. But now let us consider that these balls have enough time to reach to the terminal speed. And then I want to see what the drag force is. Okay, so what I will do, the drag force with radius r will be like this. So the drag force will be c rho a r squared, and then I have the terminal speed v squared. But at that moment that I reach to this, the speed will become the terminal velocity, then it becomes equal to the magnitude of the weight, the gravity. But then this becomes the density of the iron. So let me write F, the density of the iron, multiplied by the volume of the sphere, which becomes 4 over 3 pi r cubed, and then multiplied by g. Okay? So then from here, I can immediately calculate the terminal speed based on this empirical law. Okay, so what happens here? If I want to do that, so V becomes a square root of this divided by that. Of course, r squared and r are simplified, so it becomes 4, the density of the iron, and then times pi, and then times r, and then times g, and divided by what? C and the rho of air. So, according to this empirical law, the terminal speed should follow this rule. Okay? So what I have to do now? I have to calculate this number. It is possible because the radius of both balls are given to me. The density of iron is given. I know G, I know pi, I know 4. C is given in the problem. And the density of air in the book is given 1.2 kilograms per cubic meter. Okay, so that's also given. So based on these numbers, I can calculate V, and then I can take V with me and put it here, and I can calculate the descent time of that particular sphere. I have to calculate these 2 times. Once for the small sphere, once for the big sphere, and see what will be the difference in time of descent for those balls, and then compare them and to see what the difference is, and see that it is possible or reasonable that people at those times could detect this difference. Okay, in order to do that, I want to use GeoGebra, okay, to do that. So let us do it here. Okay, so to do this, I go to cast view, but the typing probably will be boring for you. I start the typing and pause video, complete the typing, and show you the results. Okay, so I go to cast view. In order not to be distracted by other views, I just take off this one. And then I start defining my variables. This is the way that I learned to do it in GeoGebra. So you have to first give the numbers. For example, the capital C, I put semicolon equals to, in the problem it is given to be 0.8, and then I press enter, okay? And then I have to introduce all my variables here. Okay, so I will go here and choose, let me see, what was it here? I go to Greek letters, I choose row, and then I put an index F, okay, and I put semicolon equals to, this is the, I have to write F and then come here and then put semicolon equals to 7,500 in this case, and I press enter. So I'm giving the data to the problem. As I told you, this might be a little bit boring, so let me type and then I will show you. I will pause recording now. So I'm back now. So I put this boring thing. So I just introduced, this is the way I could learn to do it in GeoGebra. If someone knows a better way, I would appreciate if you can just leave a comment. So I introduced these constants. So this is the drag coefficient, the density of iron, and then gravity acceleration and everything. And then I put the formula for the terminal velocity as we derived on the board, as you remember. That is this formula I put there. Okay, and then I also put this formula, but of course, instead of h in the problem, it was given 25 meters. So I just replaced that h with 25 meters and I typed that one. Okay, so the cast view of GeoGebra keeps everything exact, but I want to have the approximate value. So I would say that if I go here and then I press this one, I hope that I got the answer here, but let me see what the answer is. Okay, so I don't know why this is making trouble here. Okay, so it is 2.26, and if you don't mind, let me just change the setting only to 2 decimal places. I would say that probably is enough. And then this is 2.26 seconds, but be careful here. I have taken the radius to be 0.05 meters. So this is the bigger one, 5 centimeters. But now, so remember this number is 2.26, but then I will go back here and change this number to 5 millimeters. So I have to put another here, and then I will type that one, and then it becomes 2.28 centimeters. I hope that I haven't done any calculations wrong, but you see the difference is 200ths of a second. Okay, I don't know if you really had this feeling that it should be. So I mean, essentially for any practical purposes, they really come at the same time. So the difference is 200ths of a second, which probably, if I'm not mistaken, people could not detect that short interval of time back then. So even today, I mean, I would say that this is extremely small interval, and it means that essentially these two arrives at the same time. Okay, I would say that this is a nice problem. So we did some theoretical calculations and then connected to some kind of very famous experiment in the history of physics, and we get some insight about it. Okay, so I hope that this video was useful for you. So until the next video, be safe and goodbye. Thank you.